Hello, and welcome to the third video in the Swivel Embedding series. In this video, we'll take a closer look at the training objective and cost function used in Swivel. In the previous video, we discussed pointwise mutual information, or PMI, and how word embeddings can be viewed as a low-dimensional approximation of a PMI matrix. We also discussed Swivel's key idea. A zero in the co-occurrence matrix is not necessarily just noise. In this video, we'll see how this idea is translated into a loss function that we can use to train the model. We'll also take a look at the model architecture that uses these loss functions. Let's start with the simpler case where we actually observe the co-occurrence, meaning xij is greater than 0. As we saw in the previous video, the empirical PMI matrix can be computed from the observed co-occurrence counts. However, when xij is 0, the term log xij becomes negative infinity, so the PMI is not defined in the usual way. For now, let's focus on the case where xij is greater than 0. We'll call this loss the observed co-occurrence loss, or L-observed. The observed loss has the following form. We take the dot product of the word embedding wi and the context embedding cj and compare it with the observed PMI value. We then square the difference. So this is essentially a standard squared error loss. In other words, the model is trained to make the dot product of the two embeddings close to the PMI of the word pair. Because this is a squared error loss, we get the familiar U-shaped curve shown as the solid line in this figure. The horizontal axis represents the predicted value, which is the dot product of the two embedding vectors. The vertical axis represents the loss. In this example, the actual PMI value is 2.0. When the predicted value is 2.0, the loss is minimized. As the prediction moves farther away from 2.0, the loss increases. So the observed loss essentially says move the prediction toward the observed PMI. The dotted line in this figure represents the loss for the other case, where xij is 0. We'll come back to that loss shortly. Before that, let's briefly compare Swivel with Glove. As we discussed in the previous Glove series, Glove uses a loss function based on the logarithm of the co-occurrence count. Importantly, Glove only trains on pairs with positive co-occurrence counts. Pairs where xij is equal to 0 are simply excluded from the training objective. Swivel takes a different approach. For observed pairs, Swivel uses the observed loss we just discussed. For unobserved pairs, it uses a separate loss function. We'll examine that second loss in a moment. There is another interesting difference between Glove and Swivel. Glove tries to model the logarithm of the co-occurrence count. Because raw co-occurrence counts are strongly affected by word frequency, Glove introduces two learnable bias terms, bi and bj. So in Glove, the model's prediction is the dot product of the two embeddings plus the two bias terms. The target is the logarithm of the observed co-occurrence count. Swivel is different. In Swivel, the model prediction is simply the dot product of the two embeddings, and the target is the PMI value. PMI already incorporates information about the frequencies of the individual words. In particular, the PMI expression contains the terms involving log xi star and log x star j. So the frequency correction is already built into the target itself. For this reason, Swivel does not need separate word and context bias terms in the same way Glove does. There is also a weighting function, fxij, in front of the observed co-occurrence loss. The basic idea is that a pair with a larger co-occurrence count receives a larger weight. So, pairs that occur together more frequently have a greater influence during training. On the other hand, pairs that are observed only a few times receive a smaller weight. This makes sense because very small counts can produce statistically unstable PMI estimates. For example, a pair that happens to occur only once may have a very different PMI estimate if we collected a different corpus. We therefore don't want such a rare observation to have too much influence on the learned embeddings. The original Swivel paper defines fxij as follows. After experimenting with different settings, the authors report that the best results were obtained with b0 equal to 0.1, b equal to 1/4, and alpha equal to 1/2. The square root term is particularly important here. As the co-occurrence count increases, the weight also increases. But instead of increasing directly with the count, it grows more gradually according to the square root. For example, a pair that occurs 100 times receives a weight roughly 10 times larger than a pair that occurs once, rather than 100 times larger. This prevents extremely frequent pairs from completely dominating the training objective. The 0.1 floor also plays an important role. It ensures that even a pair with a very small positive count does not receive a weight of 0. So a pair observed only once is still included in training. It simply receives relatively little weight. In Glove, the weighting function is capped once the count reaches a certain value, x max. Beyond that point, the weight stays at 1. Now let's move to the opposite case. What happens when xij is 0, meaning that the pair was never observed together in the corpus? The ordinary empirical PMI cannot be used directly in this case. This is because the PMI contains log xij, and when xij is equal to 0, log of 0 approaches negative infinity. So we need a different way to handle these pairs. This is where Swivel introduces a separate loss for unobserved co-occurrences. First, the error for an unobserved pair is defined as follows. Here, PMI star denotes the smooth PMI. The basic idea behind smoothing is to replace the 0 count with a small non-zero count. In this case, Swivel uses an add-one smoothing idea. So for an unobserved pair with xij equal to 0, we effectively treat the count as 1 when computing the smooth PMI. This gives us a finite value instead of negative infinity. Add-one smoothing, also known as Laplace smoothing, is a simple and widely used technique for dealing with zero-frequency problems. Now let's think more carefully about what xij equals 0 actually tells us. If two words are never observed together in our corpus, it doesn't necessarily mean that they are completely unrelated semantically. It may simply mean that we did not observe them together in the particular corpus we are using. So we should be careful not to interpret an unobserved co-occurrence as absolute evidence of zero semantic association. Then, what does it mean to replace the zero count with 1 when computing the smoothed PMI? It gives us a useful finite reference value. In other words, we can think of it as asking, what would the PMI look like if this pair had been observed at least once? This gives the model a reasonable statistical reference point instead of an impossible target at negative infinity. There is another important aspect of this reference value. The smoothed PMI still depends on the frequencies of the two individual words. Suppose I and J are both very common words. Based on their frequencies, we would normally expect them to co-occur relatively often. If they nevertheless never occur together, that absence provides stronger evidence that their association is weak. In this case, the denominator in the smoothed PMI becomes large. As a result, the smoothed PMI becomes relatively small. To reduce the error, the model therefore has an incentive to keep the dot product of the two embeddings relatively small. In other words, the model learns not to predict a strong association between these two words. Now consider the opposite case. Suppose I and J are both very rare words. Their chance of appearing together may already be quite small, simply because they are rare. So even if we never observe them together, we cannot conclude that they are unrelated. In this case, the denominator in the smoothed PMI is smaller. As a result, the smoothed PMI can be relatively larger. The model therefore does not have to push their predicted association as strongly toward a very low value. This frequency-dependent behavior is one reason why the smoothed PMI provides a useful reference for unobserved pairs. So even when Xij is 0, we can still incorporate that pair into the training process. The authors then apply a soft plus function to this error to define the unobserved co-occurrence loss. This is denoted as L unobserved and can be written as follows. This gives us the soft hinge-like loss shown by the dotted curve in the figure. The important point is that the model does not need to match one exact target value for an unobserved pair. Instead, once the predicted value is sufficiently low, there is little reason to push it any lower. In other words, Swivel is saying if the predicted association is already low enough, that's good enough. The model only receives a strong learning signal when the predicted value becomes too large. So, the unobserved loss mainly prevents the model from predicting an excessively strong association for a pair that was never observed together. We can now combine these two loss terms as follows. The total Swivel objective is the sum of the losses for observed and unobserved co-occurrences. For observed pairs, the model learns to match the empirical PMI. For unobserved pairs, the model learns to avoid predicting an excessively strong association. So these two loss functions work together to form one unified objective. This is how Swivel turns the idea of noticing what's missing into an actual mathematical objective. At this point, a natural question comes up. If we include not only observed entries but also unobserved entries, doesn't this become computationally expensive? The answer is yes. If the vocabulary is large, the full co-occurrence matrix can contain an enormous number of entries. And unlike methods that only process observed pairs, Swivel also needs to consider the unobserved entries. So the computational cost can become very large. To address this problem, Swivel uses a shard-based training structure. Instead of processing the entire matrix at once, the matrix is divided into smaller blocks, or shards. These shards allow Swivel to perform the computations efficiently and in parallel. We'll take a closer look at this block-based matrix partitioning and distributed training structure in the next video. Finally, let's briefly look at the Swivel model architecture. The overall structure is similar to the architecture we saw in Glove, so we won't go into every detail here. As in Glove, the model consists of a word embedding matrix and a context embedding matrix. However, unlike Glove, the original Swivel does not use separate word and context bias vectors. The reason is that Swivel directly models PMI as its target, and the frequency information that Glove handles through its bias terms is already incorporated into the PMI target. Another important difference is how the training data are treated. Glove trains only on observed co-occurrence pairs. Swivel explicitly models both observed and unobserved co-occurrences. According to the author's experiments, this approach leads to better embedding performance than several competing approaches. So in this video, we looked at the Swivel objective function and its model architecture. In the next video, we'll look at block-based matrix partitioning for distributed training. We'll see how Swivel makes this large-scale training process computationally practical. Thank you for watching, and I'll see you in the next video.